after a little downpour, when sunlight strikes the earth, there is a formation of a remarkable montage of colors called rainbow. Isn't it an awe-inspiring sight? Those beautiful 7 colors. But do you know that this formation of rainbow is known by a special name in chemistry? Let's find out in today's episode. Hello, I am Deobrata Goswami. Welcome to the colorful world of chemistry. Today we have a multi-hued episode for you, so buckle up and let's see what's there to learn today. In this episode, we will study about atomic spectra, line spectrum of hydrogen, Bohr's model for hydrogen atom, and limitations of Bohr's model. Then we will take a look at some important questions and their answers in the exam decoded section. You all must agree with the fact that a rainbow is the most spectacular light show in the whole of nature. But there is a whole lot of science involved in it. Let me tell you. A rainbow is formed when light from the sun is refracted into 7 beautiful colors. It is made of a multicolored arc with red on the outer part of the arc and violet on the inner section. A similar phenomenon can also be observed when white light is passed through a prism. When a white light is passed through a prism, it splits into a series of colored bands known as spectrum. The 7 colors included in the spectrum are violet, indigo, blue, green, yellow, orange and red, which are commonly known as Vibgyor. But can you tell me, what does this splitting of light into a series of colored bands mean? Well, it means that white light is composed of waves of different wavelengths in the visible region. The prism bends the light of different wavelengths to different extents. Let me elaborate on this. The red colored band, which has the longest wavelength, is deviated the least, while violet has the shortest wavelength and hence is deviated the most. This spectrum of white light, which consists of all wavelengths in the range starting from 400 nanometers to 750 nanometers, is called the continuous spectrum. In the continuous spectrum, all colors merge with each other. Another example of a continuous spectrum is an electromagnetic spectrum. Let us understand what an electromagnetic spectrum is. An electromagnetic spectrum consists of a range of electromagnetic radiations arranged in the order of increasing wavelengths or decreasing frequencies. It extends from gamma rays to radio waves. It covers all wavelengths from thousands of kilometers down to a fraction the size of an atom. Wavelengths of gamma radiations are comparable to the diameter of atomic nuclei, and that of radio waves are comparable to that of a building. Let's study the behavior of the electromagnetic radiations when they interact with matter. When these electromagnetic radiations interact with matter, the atoms and molecules may absorb energy and reach a higher energy state. Since the higher energy state is unstable, they return to the more stable energy state by emitting the absorbed radiation in various regions of electromagnetic spectrum. The spectrum of radiation emitted by a substance that has absorbed energy is called an emission spectrum. The atoms, molecules or ions that have absorbed radiation are said to be excited. However, the emission spectrum does not show a continuous spread of wavelength. Rather, the atoms emit light only at specific wavelengths with dark spaces between them. Such a spectrum in which only specific wavelengths are present with dark spaces between them is known as a line spectrum. That was about the emission spectrum. But what about a spectrum when the substance is not in an excited state?
Then we get an absorption spectrum. To obtain absorption spectrum, radiation is passed through a sample of material. The sample absorbs radiation of certain wavelengths. The wavelengths which are absorbed are missing from the continuous spectrum. Due to this, dark spaces are left and an absorption spectrum is obtained. This is also a line spectrum.
In the line spectra of an atom, each wavelength is identified by a bright line in the spectrum, and this study of emission or absorption spectra is known as spectroscopy. If you want to know more about this, you should join IIT Kanpur and come to study in my spectroscopy lab. But that's later. For now, you can log on to www.topperlearning.com. Talking of spectroscopy, there were two scientists behind the discovery of this science. Why don't you try and find out their names while I take a short break? Stay tuned, because coming up after the break is more on spectrum and what it means. Hi, welcome back to Chemistry. I am Deobrata Goswami. Let's continue our journey to understand atomic spectra. Before the break, I asked you a question. Can you name the scientists who discovered spectroscopy? And the answer is, it was Robert Kirchhoff and Robert Wilhelm Bunsen who discovered spectroscopy. Now, let's move on and study the line spectrum of hydrogen. Just as you are finding the idea of analyzing matter by using light fascinating, likewise, when scientists first detected the line spectrum of hydrogen in the mid-1800s, they were also fascinated by its simplicity.
The lines in the emission spectrum of hydrogen are classified into 5 series: Lehman series, Balmer series, Bastian series, Brackett series, and Pfund series.
Let me tell you more about the series of lines in the spectrum of hydrogen.
The first series of lines corresponds to N1 is equal to 1 and N2 equal to 2, 3, 4 and so on. This is known as Lehman series and it appears in the ultraviolet region. Similarly for Balmer, Bastian, Brackett and Pfund series, N1 is equal to 2, 3, 4 and 5 respectively. These series lie in different regions. Let us see. Lyman series lies in the ultraviolet region, Balmer series lies in the visible region, while Bastian, Brackett and Pfund lie in the infrared region.
It seems that one of our viewers have a doubt. Let's hear it.
Hello sir, I am Ritesh, and I was wondering that though hydrogen contains only one electron, why does it show many lines in the spectrum?
This is indeed a good question. Well, let me explain it.
You know that in a sample of hydrogen, there are a large number of hydrogen molecules. On passing electric discharge, they split into hydrogen atoms. Therefore, electrons of different atoms absorb different amount of energies and are then excited to higher energy levels. Now, the electron can jump from excited state to ground state in either one jump or many jumps, and each jump associated with a definite energy emits radiation of different wavelength. As a result, each wavelength appears as different lines in spectrum. In 1885, a Swiss schoolteacher, Johann Balmer, showed that the wavelengths of the visible lines of hydrogen fit in a simple formula in terms of wave number.
Later, on further research, additional lines were found to occur in the ultraviolet and infrared regions of the hydrogen spectrum.
Soon, Balmer's equation was extended to a more general one called the Rydberg equation, which allowed the calculation of the wavelengths of all the spectral lines of hydrogen. In this formula, nu bar is the wave number of a spectral line. 109,677 centimeter inverse is called Rydberg constant, and N1 corresponds to lower energy levels and N2 corresponds to higher energy levels.
Now, let's take an example to get a clear picture. What is the wavelength of light emitted when the electron in a hydrogen atom undergoes transition from energy level with n is equal to 4 to energy level with n is equal to 1?
Applying the Rydberg's equation, wave number can be related to energy levels by the formula shown. Given that N1 here is 1 and N2 is 4. On substituting the values in equation, we get the value of wave number as 102,822 centimeter inverse. Since wave number is the inverse of wavelength, we can easily find the wavelength. As a result, the wavelength becomes 97 nanometer.
Now, in order to explain the line spectrum of hydrogen, Niels Bohr proposed some postulates.
According to Bohr, an electron in the hydrogen atom can move around the nucleus in a circular path of fixed radius and energy. These paths are called orbits or energy levels. These orbits are arranged concentrically around the nucleus. Now, as long as an electron remains in a particular orbit, it does not lose or gain energy and its energy remains constant. That is why these orbits are also called stationary states. When transition occurs between two stationary states, the frequency of the radiation absorbed or emitted can be calculated. If the two stationary states differ in energy by delta E, which is equal to E2 minus E1, then the frequency of the radiation is equal to delta E divided by the Planck's constant h. Note that E1 is the energy of the lower energy state and E2 is the energy of the higher energy state.
Moving on to the next postulate.
The next postulate states that an electron can move only in those orbits for which its angular momentum is an integral multiple of h upon 2 pi. That is, if the angular momentum of an electron is MeVr, then the electron will move in only those orbits for which MeVr is equal to h by 2 pi or 2h by 2 pi, 3h by 2 pi and so on. 1.5h by 2 pi is not possible.
The Bohr's model developed by Niels Bohr for hydrogen atom could explain various observations.
Bohr calculated the energy of an electron in the nth orbit of a hydrogen atom by the formula shown. The integer n is called the principal quantum number. It can have values from 1 to infinity. Now, each orbit corresponds to a different value of n. The radius of the orbit gets larger as n increases. The energies of the electron of a hydrogen atom given by this equation are negative for all values of n.
Now, according to this formula, the more negative or lower the energy, the more stable the atom will be. That means the energy is most negative or lowest when n is equal to 1. And as n gets larger, the energy becomes successively less negative and therefore increases. Some important points to take into account are: the lowest energy state is called the ground state of the atom, and when the electron is in a higher energy state, the atom is said to be in an excited state. Now a question for you: what happens to the energy of an electron as n becomes infinitely large, and what information does that give us?
Take a look at your screen. If we put the value of n as infinity in the given equation, energy becomes 0.
And energy becoming 0 means the electron has become free from nucleus. At this state, hydrogen atom gets ionized. You know that one of the biggest successes of Bohr's model was the explanation of hydrogen spectrum. According to one of the postulates of Bohr's model, only orbits of certain radii corresponding to certain definite energies are permitted for an electron in a hydrogen atom.
As I told you earlier, energy must be absorbed for an electron to move to a higher energy state. Conversely, radiant energy is emitted when the electron jumps to a lower energy state. So, if the electron jumps from an initial state that has energy EI to a final state of energy EF, the change in energy is given as delta E. Substituting energy expression for initial and final state in the equation, we can easily calculate the energy of the electron. In case of absorption spectrum, NF is greater than Ni. Therefore, the term in bracket becomes positive. Whereas in emission spectrum, Ni is greater than Nf, which makes the term in bracket negative. Now, associated frequency can be given by the expression shown. And in terms of wave number, it can be given by this expression.
You must have noticed that this expression is same as the Rydberg's expression. You know, while the Bohr's model offers an explanation for the line spectrum of the hydrogen atom, it has also got its own limitations. Like, Bohr's model failed to account for the finer details of the hydrogen atom. For instance, splitting of a line in the spectrum into two closely spaced lines. This could be observed by using spectroscopic techniques. Besides that, Bohr's model was also unable to explain spectrum of atoms containing more than one electron.
Further, Bohr's model was unable to explain Zeeman effect, that is, splitting of spectral line in presence of magnetic effect.
Bohr's model also failed to explain Stark effect, that is, the splitting of a spectral line in presence of electric field. Therefore, we need a better theory which explains various characteristic features of atoms having many electrons. Now, let's take a little break to get all this knowledge assimilated. You can also check out our website www.topperlearning.com for more questions, info and tips. But don't go away, as we have the much awaited exam decoded after this break. Welcome back. I am Deobrata Goswami and you are watching Chemistry 11. Today we studied about spectrum. Next up is the exam decoded. But before that, let's do a quick recap of all that we studied today.
In today's episode, we studied that when a ray of white light is passed through a prism, it is split into a series of colored bands called a spectrum. A spectrum of radiation emitted by a substance that has absorbed energy is called an emission spectrum. There are 5 series of lines in the spectrum of hydrogen. According to Bohr, an electron in the hydrogen atom can move around the nucleus in a circular path of fixed radius and energy. These paths are called orbits. One of the limitations of Bohr's model was it failed to explain the splitting of a line in the spectrum into 2 lines, which was obtained using spectroscopic technique.
On to the much awaited exam decoded. Welcome to Exam Decoded. Here, we will assess your knowledge and preparation. So brace yourselves. First up is the rapid fire round, where you will get 5 seconds to answer each one of the 5 questions. Let's fire it up. Here is the first question. Which part of electromagnetic radiations has shortest wavelength? A. Gamma rays, B. X-rays, C. UV rays, D. Visible rays. The correct answer is A. Gamma rays. Now the second question. Electromagnetic spectrum is a continuous spectrum. True or false? The answer is true. Moving on to next question. The spectrum of hydrogen atom contains A. 2 series of lines, B. 5 series of lines, C. 6 series of lines, D. 8 series of lines. The correct answer is B. 5 series of lines. Now the next question. Bohr's model could easily explain spectra of atoms containing more than one electron. True or false? This statement is false. Last question. According to Bohr's model, an electron can move only in those orbits for which its angular momentum is an integral multiple of A. 2 pi, B. h upon pi, C. h upon 2 pi, D. pi. The answer is C. h upon 2 pi. I hope you all did well. Now let's check your scores according to this scorecard. If you got all the questions correct, then you are a high flyer. If you got 3 to 4 correct, then you are an achiever. A bit of revision and you can do wonders. But if you have scored less than that, not to worry. Some more hard work and you will be at the top. And you can also log on to www.topperlearning.com. Now, let's analyze this topic from exam point of view and see what can be expected. The topic spectrum comes under the unit structure of atom, which carries a weightage of 6 marks. This makes it critical from the exam point of view. The questions asked from this topic can be very short answer type questions for 1 mark and short answer type questions for 2 or 3 marks. The questions covered from this topic can pertain to numerical ability. Besides good foundation, you also need to know the ideal way of answering a question. So, let's learn the ideal way of answering by taking up this example based on Bohr's model. Applying Bohr's model, calculate the energy and frequency of radiation emitted when an electron in hydrogen atoms returns from 5th energy level to 2nd energy level. To find the energy, we use the relation between energy and various levels. Here, Ni is equal to 5 and Nf is equal to 2. Substituting the values, we get value of energy. This step gets you 1 mark. Now, since energy and frequency are related by the equation delta E is equal to h nu, substituting the value of Planck's constant, we get the value of frequency. Doing this correctly will fetch you another 1 mark. If you keep practicing questions like these, there is no doubt that you will outshine your exams. You can also head over to www.topperlearning.com, where you will find many more such questions. Today we learnt a lot about spectrum and Bohr's model. It's time to wrap up, but before parting, I would like you to solve this brain teaser. Which is more harmful to human skin, visible light or X-rays? Think. Alright, I will answer it. As you know that visible light does not penetrate the human skin. X-rays on the other hand can penetrate. Hence, X-rays are more harmful to skin. Always remember that the penetration effect of any radiation depends on its wavelength. Shorter the wavelength, greater is the penetration power. That's all for today. Wishing you success with rainbow colors. Until next time, goodbye and keep thinking.